defense. Very similar terms, very similar algorithms that are used for guidance and so on down the line. So this is very familiar territory for me. So the DART mission, DART stands for Double Asteroid Redirection Test. The double asteroid comes in where what they have done or chosen for this test was to hit one asteroid that's in orbit around another one. So that's where the double asteroid term comes from. Redirection is basically trying to change the orbit or the velocity of the asteroid so that by the time it makes it to the Earth's orbit, it will have been deflected enough that it would miss the Earth in the case of an asteroid that was coming to the vicinity of the Earth. In fact, this whole thing has to do with planetary defense. It's the very first full-scale test of a kinetic impactor for asteroid deflection that NASA has ever undertaken. And what's interesting about this is that when you think of all the different natural disasters, there's only one that can be prevented, at least as far as we know of today, and that is preventing an asteroid from hitting the Earth. This mission was basically a demonstration of that fact, that we can actually send something that will change the orbit of an asteroid enough that it will miss the Earth instead of hitting it. So it's a very important test. Now, the purpose, as I mentioned, is, you know, when we go to send a probe that hits the asteroid, we need to make an assessment of how effective that is to deflect the asteroid enough to, you know, avoid hitting the Earth. So the whole thing is basically based on determining how much of an asteroid's momentum is changed by hitting it with an impactor. The mission is under the NASA's Planetary Missions Program Office. It's managed by Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. It was launched on November the 24th by a Falcon 9 from Vandenberg Space Force Base. And what's interesting here is when you look at the cost, all the sources basically refer to about a $325 million cost. That cost does not include the launch services, interestingly, and that's due to the fact that SpaceX, which is the manufacturer of the Falcon launch vehicle, has an agreement with NASA that would be in a separate pot that would not be allocated to a project. So when you see that $325 million cost, it does not include the launch services. Now, here's a diagram that shows all the different types of methods that we have right now, or possible methods that we could eventually draw upon to deflect an asteroid. If you look at the very bottom of the chart, there's the kinetic impactor, and that's what DART was all about. So here's the question. And in fact, let me go back to the very first chart here. Look at what I have over here for the purpose. Determine how much an asteroid's momentum is changed by an impactor. Well, when you think about it, isn't that something that a high school kid can do if, you know, who's taking physics and algebra in high school? Here's the equation right here. You just use the conservation of linear momentum. Momentum before the impact is equal to the momentum after the impact. You write the equations relative to the spacecraft and the target, which is dimorphous, And it's very simple. You can solve for delta V and there's nothing to it. So the question is why would NASA spend so much money to determine how much momentum is imparted to an asteroid by impact if a high school student can determine that, sitting in a classroom for doing it in about 15 minutes. So the question is, what are we missing? Well, the problem is that the answer to that is that this equation is incorrect as written. There's something missing. And in fact, this problem is so difficult that engineers and physicists have been working on this for many, many years and still do not have a full accounting of it. They're using high-powered computers to try to get a handle on it, in fact. So here's the answer to it. What's missing is the ejecta. When you have an impactor that hits an asteroid, what you're going to have is you're not going to just have something that's going to merge into the asteroid. You're going to have a lot of ejecta, a lot of junk that's going to be ejected from the asteroid, which is going to add to the momentum of the spacecraft that hits it. In fact, one thing that I think is kind of interesting, look at what happens with light. Take two photons, two identical photons with the same energy, the same frequency, the same wavelengths. One of them hits an object that is completely black and is absorbed by the object. The second photon hits an object that is reflective and completely, reflects the photon off the surface. Which case provides more momentum to the object? Is it the case where the photon gets absorbed or the case where the photon is reflected? And the answer is that a photon that's reflected will impart twice the amount of momentum as a photon that is completely absorbed by the target. It's very interesting to note that. And the same thing holds true here. The more ejecta that is thrown out, the more delta V that's imparted to the asteroid. And in fact, if you look at all the different things that you have to account for to come up with an estimate for the momentum that's imparted by the ejecta, you have to account for all these different variables. It's just a maze of things. And like I say, NASA has spent many mucho dollars developing various codes to come up with an estimate for the momentum that's imparted to the asteroid by the ejecta.
That seems counterintuitive.
It does. This is a very interesting case. They always talk about rocket science as being a tough thing. This is a case in point. On the first guess, you would think, hey, this is a very simple thing. I can do that with a pencil and paper in no time. When you give it a little bit more thought, there's a heck of a lot more to it than what meets the eye. There's many instances like this where on first thought, you think that it's going to be a cinch to do, but on further analysis, you find out, hey, there's a lot more to this than what we originally thought. So here's something that I think is very, it illustrates the problem very closely. If you look at this, we have two instances where we have the spacecraft hitting an asteroid. The one on the left shows the spacecraft hitting an asteroid that has a very strong surface, or basically a strong internal structure. The picture on the right is what happens when the same spacecraft going at the same speed, coming in at the same angle and everything else, hits a weaker asteroid that does not have the strong internal strength that the first asteroid has. You can see by the illustration that there's a lot of difference between the sizes of the impact crater that's formed. The one on the left does not produce much additional momentum. The one on the right, however, you can see has a lot more material that has been excavated, which causes more material to be thrown out, which produces an additional, a lot more force reacting onto the asteroid and causes more of a velocity change. And this is some details on the DART spacecraft and impactor. Actually, there were two spacecraft that were involved. The first one was the impactor itself. That's called DART. The second one was a companion spacecraft, which was a CubeSat built by the Italian Space Agency. Looking at the DART spacecraft impactor, it's kind of interesting. This, basically all that NASA had to do was to come up with a very simple design to impact this, impact an asteroid. Shouldn't have cost them a lot of money to develop. What they did though was, even though it's a very simple design, they had a very interesting array of cutting edge technologies for different things like communications. They have an antenna that has never been flown before. It's called the Radial Line Slot Array, RLSA. It's a very interesting design. It's an antenna that can not only pick up signals, but can transmit the signals at from the same antenna. For the propulsion, they used a very high-tech, one-of-a-kind ion rocket engine using xenon propellant. They had in their avionics, they had a single board computer and interface module. Electric power, they had 2 rollout solar arrays that had never been flown on a spacecraft before. But this is one of the things that NASA does periodically, just like on the Dawn mission to, I think it was to Ceres and other places like that. They take the opportunity to test various technologies so that they can advance the state of the art for future spacecraft. And this is a typical example. But anyway, if you look at this, the only science instrument that was on the DART spacecraft was a camera. And that camera basically had a dual use. One was to take pictures as it was coming in for the impact into the asteroid. The second use was for, it was a sensor for for navigation. So they got their money's worth on that one. The companion spacecraft basically was nothing more than a platform for cameras that was to be used to get good estimates of how big the crater was that was formed by the impact. And here's a picture of the impactor on the left and the CubeSat on the right. Now the target was the asteroid Dimorphos. The name means 2 forms in Greek. It was chosen in anticipation of its changes, it changes to the asteroid as it would be known to us in 2 different forms. One would be the form that we saw it before DART hit it, and the second form would be the form that it would be in after DART hit it. There's a follow-on mission that the Europeans are going to be sending called Hera, which will show the actual impact crater in a few years. And the asteroid is those 2 asteroids are members of what are called the Amor group of asteroids. They're asteroids that orbit between the Earth and Mars. The second asteroid was Dimorphos. That's the bigger one. It's about 5 times bigger than I'm, s- uh, I'm sorry. I'm sorry, hang on here. Let's see here. Oh, I see what I had. Okay, I missed the description on the second asteroid was Didymus. That means twin in Greek. Was discovered in 1996. But there's a very good reason why Dimorphos was picked for the target. It's very small, so you get more of an effect on the change of the velocity of the asteroid when it's hit. It's close to the Earth, and it orbits another asteroid. And that is by far the biggest reason, orbiting another asteroid. When you look at the effect of the, change in momentum of the asteroid that's hit, you're talking about a change in velocity about, on the orders of less than a millimeter per second. Very, very small. What's interesting about an asteroid that's hit, that is in orbit around another asteroid, is that the orbital period, even though you have a small velocity change, is going to give a change in the period of, on the order of several minutes. And that's very easy to detect by looking at the time differentials between eclipses as seen from the Earth. What happens is the small asteroids that is impacted will be eclipsed by the bigger asteroid, and all you have to do is time the eclipses, and you'll be able to find out how the period has changed. So it's a very, very good method to get a good handle on what the change in the momentum is. So here's a rundown of the two different asteroids that were involved here. If you look over on the right-hand side in the middle, you see the dimensions. The mean radius of Dimorphos that was hit was only 85 meters. So it's a very small object. And the impact itself, well, let's see. Well, you look over here for the escape velocity from Dimorphos, about 8.8 centimeters per second, or about 0.2 of a mile per hour. Virtually all the ejecta that are formed from the impact reach escape velocity. So you're throwing out all this junk from the impact and never to be seen again.
So Ken, I have a question.
Yes.
So I presume it's continuing to be observed. Has the flight trajectory of the binary system, has that been altered by the impact, or are you just seeing a change in the orbit and the eclipsing as you described, a few minutes ago?
Okay, now I didn't get the very first part. You're asking about, did it change what?
Did the impact change the vector, I guess is the correct term, of the entire binary system? I mean, has that been observed and measured? In other words, did it move the entire, orbiting binary system?
Okay, that's a good question. I suspect that the answer to that is yes, but a very, 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 very small amount. It's probably not detectable. What's really important in this test was how much of a change was
Imparted.
would happen to the object that was impacted.
Right.
That's the whole thing. And that impact was very, very slight. I mean, it had very slight effect. In fact, I'll get to that later on. But this method of actually hitting an asteroid that's in orbit was a brilliant idea, because it alleviated the team from having to determine a very small velocity change to just determining, the change in a period of an orbit. That's a lot easier to do than a velocity change.
I believe you said earlier that the smaller body was like 1/5 the size of the larger body, correct?
Yes, that's right.
So the movement of the orbiting system must have been a complicated flight as well. And so the navigation of the impacting a spacecraft must have, the navigation must have been impressive.
Well, let me tell you something, like I mentioned at the beginning, I worked on missile defense. And my director was Dr. John Pillar, very famous guy. John used to say that hitting, a lot of people would say that missile defense is nothing more than hitting a bullet with another bullet. Well, there's a lot more to that than that. Hitting a bullet with another bullet is a very simple thing. That problem was solved years ago. To give you an idea of how difficult missile defense is, just telling you the fact that hitting a bullet with another bullet is the easy part gives you an idea that, it's a very difficult problem. But in this case, that was the problem. All you had to do was to hit another bullet with another bullet, and that is easy. There's something that's called proportional nav that's used in missile defense. And the proportional nav basically is just keeping the same angle to the object that you want to hit with your interceptor, and eventually you're gonna hit. That's what they did on this mission right here. They used the same equations for guidance as is used in missile defense, proportional navigation. And that was a very simple thing to do. You think that this interceptor basically flew from the Earth and hit within 17 meters of the target on an asteroid 11 million miles away. That's incredible. But the close in trajectory was very simple to achieve using the proportional nav. All that you needed to do was get somewhere in the vicinity, and once you got the target in the camera view, you could hit it. There'd be no problem. And that's exactly what happened. Something to think about. Anyway, here's a picture that was taken by the onboard camera called Draco on the impactor. The big object on the left is Didymus. That's the main asteroid. And then Dimorphos is over there in the upper right. You can see that Dimorphos is quite a bit smaller than Didymus. Now here's a very interesting picture. If you look at the very center of this picture over here where we're looking at Dimorphos, if you look in the center of this box, there's a red object. If you go and look at a later picture that was taken by Draco, you'll see that red object basically is nothing more than a Tesla Roadster. So we now know what happened to Elon Musk's Tesla. It's right there on Dimorphos. Now, I hope you don't.
So they didn't send a DART.
Anyway, that's the car I was talking about at the very beginning. This obviously was just put in there by an artist to indicate the size of the objects that are in the view. And you can see that this picture right here that's blown up, that was the last full frame picture that was taken by the impactor before it impacted the asteroid. But you can see about how big these boulders are compared to the sky, to the car there. That was taken about 11 seconds prior to impact. Oops, hang on here. So the impact right here. Now this is the interesting part right here. The impact speed was about 6.1 kilometers per second, about 14,000 miles an hour. the energy that was produced by the impact was about equivalent to 2.5 tons of TNT. And that 2.5 tons of TNT, as you'd expect, is going to throw out a lot of ejecta. And based on the pictures that I'll show you in a few seconds, it looks as though it actually did its job pretty well. But here's the interesting part. If you look over here on the predicted effects, the orbital speed change is less than 0.002 miles per hour, about somewhere on the order of about 0.5 millimeters per second. Very, very small, very difficult to detect by radar. The orbital period change, though, they were expecting somewhere between 4.2 and 10 minutes. So that's a lot easier to determine based on eclipse timings. And then the orbital altitude change that accompanied that would have been something on the order of about 20 feet or so. Now here's a picture that was taken by the CubeSat. You can see that the impact was, throwing out a lot of debris as expected, and that's good. That is very hopeful. If you look over here on the previous picture, Dimorphos is basically nothing but a rubble pile. And that's good because what happens is, since it's just a bunch of stuff that is, mingling them, around each other, they're, fairly loosely connected. That means that you can easily jostle that stuff around and eject it out. And that is good news when it comes to trying to deflect an asteroid. So I think that JPL and also the laboratory there at Laurel is hoping that they're going to find out that they had quite a big of an impact and change in the momentum of the asteroid. And like Gary was saying, I got some pictures here. The pictures on the left are pictures that were taken by James Webb Space Telescope, and the ones on the right are the images captured by the Hubble. So you can see that you can see very clearly that there was quite a lot of ejecta that was thrown out from the impact there. And in fact, not only has there been ejecta, but it looks as though Dimorphos has actually developed a tail, and here's some images taken that show that. And then that's about the end of that.
So Ken, so when will they know exactly if they achieved their goal?
Well, that's an unknown. What they have, there's something I missed over here. Let me just show you right here. They have a lot of space-based and ground-based observatories that are looking, taking pictures all the time, trying to get a handle on not only the delta V that was imparted by the spacecraft on the asteroid, but also trying to determine what the nature of the ejecta were. The dust. Basically, you have dust and you have volatiles, and what they're trying to do is determine what the speed and the direction, the size distribution, and things that type were. But if you look over here at the observatories, oops, hang on here. You have obviously the Lysiak cube, the CubeSat that has had its own cameras taking pictures. You have James Webb, Hubble. There's also some radar arrays, ALMA and ATLAS. They're looking at this in all kinds of different wavelengths, infrared, visible, radio. So there's a lot of different telescopes that are being used, and hopefully they're going to be able to get this all put together and come up with their best estimate. But obviously there's a lot of data involved here, and they just don't know how much longer it's going to take for them to actually get this all put together and and come up with their best estimate. I suspect it's going to probably take at least another month or so. Just
Okay.
have to wait and see.
So, a question, in the photos that we saw taken by Webb and Hubble of the tails, can we assume that those will dissipate as the particles scatter? Because they have their own separate, now
Yeah,
vectors and
I'd expect that to be the case. I would think that over time, now see the picture that was taken over here on the left-hand side was taken 29 hours after impact. The one over on the right-hand side was taken two days after impact. You can see that the tail has grown somewhat in that length of time.
yeah, different quality in the photos, but yeah,
Yes.
certainly looks like a larger structure.
Yeah, I think so. And I think I would expect that that would be the case, that those tails will dissipate over time and eventually you won't see anything. But it'll take some time for that to happen.
I have another question that you talked about earlier about the equipment, the RLSA antenna. Is that like a single structure from which reception and broadcast transmissions go through, or is it two separate antennas just arranged in a single structure?
Yeah.
Two integrated.
Okay, there's the RLSA is a single high gain antenna. And I'll tell you the truth, I think if you look in this picture on the left-hand side, if you look over on the right-hand side of the main body, there's something that's protruding out. That might be the antenna. I'm not too sure.
Okay.
But it's only one. There's only one antenna, and it's used for both incoming and outgoing communication.
I see.
And I think the spacecraft on the right obviously has its own antenna also. That one is transmitted in X-band.
All right. Thank you.
Okay, thank you, Gary.
Yeah, that's